All right, you guys, so we're gonna start with a little warm up today, and I actually want you to cap your marker because we're gonna start with a number talk, okay? This number talk, since we're just doing it with the 5 of us, is gonna be kind of a short number talk and a quick one, but we're gonna get started. When you think you know the answer, just give me a quiet thumbs up and we'll go around and share. Okay, so we're gonna start with thumbs up when you think you know it. All right, Andrew, what'd you get?
480.
480. I saw lots of thumbs very quickly on that one. Who can share just quickly, how do you know it was 480 and how did you know it so quickly? Dean?
If you multiply anything by 10, you just add a 0.
Ooh, so we're looking for a pattern. Does anyone want to add to what Dean said? When we're multiplying by 10, we add a 0. Can anyone put it into their own words if you can't add to it? Ella?
You could just multiply 48 times 1 and add a 0.
Okay, so multiply 48 times 1 and then add a 0. All right, let's try another problem. Okay, what would go in my blank? What is the missing value? Carter, what do you think?
100.
Okay, 100. Did anyone have any different answers? Okay, who could support 100? Matthew?
Yeah, if you multiply anything times 100, you just multiply 48 times 1 and then add 2 zeros.
Okay, so the similar pattern. If we're multiplying by 100, we just multiply by 1 and then we add 2 zeros. All right, let's keep that pattern in mind as we try another one. This time, I'm going to use a variable for my unknown value. Okay. Oops. What is the value of my variable A? What would that value be? Ella, what'd you get?
I got 10.
10, okay. So A equals 10. Ella, can you tell me how you got 10?
So I know 10 times 10 is 100. And then if you multiply 48 times 100, it's 4,800. And
Okay.
then to equal 48,000, you just add one more 0, so I know I just put 10 because that has been 10.
Okay, so you had to have one more 10. I saw a couple me too's. Good. Anyone want to add to that? Carter?
So when you were writing the problem, I saw 2 10s, so I was like, okay, that's 10 to the second power, so I just quickly transferred that to 100, and then times 48, I saw that it was 48,000. So then I was like, well, you have to multiply that by 1,000 because you have to add 3 zeros, so I thought, well, it has to be 10.
Awesome. Can anyone add to what Carter said? If we wanted to actually make this part a little bit shorter, instead of writing 10 times 10 times 10, what could we write instead? Dean?
10 to the power of 3.
Good, 10 to the power of 3, or 10 to the third power. Very good. Okay, and really quick, let's just review. We've been working on exponents. We did it in our alien numbers project, and we've been doing it all year. So which number is our base number? Which number is our base number?
10.
10, and what does that mean, Matthew?
It means 10 is the number that you're actually multiplying.
Okay, 10 is the number that you're actually multiplying. Can anyone add to that definition of base? What does base number mean? Dean?
Like the root of it.
Ooh, the root of it.
Like, not the square root. The square root's way different. Like, the base. Like, you multiply it by, you start with it.
Okay, I see what you mean by root. It's that starting number. It's what you're starting with. And then you said something too, Matthew. You multiply it by what?
Itself.
By itself, good. And then what does the exponent, or the 3, tell us? What does the exponent tell us? Ella?
That's how many times you're multiplying it by itself.
Good, say that one more time for us, a little louder.
It's how many times you're multiplying it by itself.
Good. So it's how many times you're multiplying the base by itself. So we're going to multiply it by itself 3 times. So could we take this equation and rewrite it as 10 to the 3rd power times 48 equals 48,000? Thumbs up if you agree, thumbs down if you disagree. Could we rewrite our equation in this way? Okay, Matthew, do you want to add something?
Scientific notation of the number.
That is the scientific notation of the number. That was a great way to bring that vocabulary in there.
I got it right this time.
There you go. Good job. So now that we've reviewed this, I want to take a look at just one more thing. Okay, just one more thing. I noticed that as we went through the problem, we started with 480, and then we went to 4,800. How many times greater is 4,800 than 480? How many times greater is this one than this one? Andrew?
10.
10 times. How'd you know it was 10 times greater?
Because I added a 0 to 480 and I know that would be 10.
Okay, you added a 0. Can anyone clarify what he means by adding a 0? What does he mean by adding a 0? Matthew?
Well, since 100 is 10 times greater than 10, you know that since one of the factors is 10 times greater, you know that the product is going to be 10 times greater.
Awesome. So the product will be 10 times greater, and because of that, that's where that 0 comes from. Very good. We have to be careful when we say add a 0, right? Because technically, if I do 480 plus 0, did I change the value of the number? No.
Adding a 0 to the number without addition.
You're adding it to where? Where are you adding it? Ooh, you're adding it to the end of the number, which does what to the place value?
Makes it 10 times greater.
Which makes it 10 times greater. Think about the place value it ended in. If we just look at 480, what place value is the 4 in? The hundreds place, right? And by adding a 0 or placing a 0 at the end of the number, what place value did that push the 4 into, Andrew? The thousands place. And let's look one more time at 4,800. Now, what place is the 4 in? Dean, can you tell us what place the 4 is in now?
The 10,000s place.
The 10,000s place. Very good. So we had another 0 at the end of the number, which pushed it 10 times greater into the 10,000s place. What we're going to be doing is we're going to add on to this idea. We're going to be thinking about using exponents and actually the properties of operations to help us with some of these area problems that you guys are doing in class. So we're going to sort of mix a lot of things that we've been working on. Really great number talk, you guys. So who can tell me, when you were working on the cheetah enclosure, what was the area of the cheetah enclosure that you were trying to find? Who remembers what that was? Carter?
It was 4,800.
Okay, good. It's almost like I knew what number you guys were going to use, right? So we were looking for 4,800. On your whiteboard, everybody write for me at least 2 different factor pairs that you can think of for 4,800. It could be one you already used in class, it could be a different one, but give me at least 2 different factor pairs for 4,800. And you can show me your board when you think you have them, just so I can see what we're working with. Good. And I see you got more. That's awesome. Okay, very good. Now, before we share these out, okay, I want to talk about this number 4,800. If I were to rewrite this using an exponent like we just did, how could I rewrite 4,800 by multiplying something by a power of 10? How could I rewrite 4,800? Matthew?
Well, it would be 48 times 10 to the second power.
48 times 10 to the second power. And how did you know it was 10 to the second power?
Because 10 to the second power is 100, and 48 times 100 is 4,800.
Good. So we could look at this as being 100, and 48 times 100 is 4,800. We're going to use that to help us with some of these factor pairs. Now, you all came up with some great ones, and I noticed I want to borrow the factor pairs you had, Andrew. So can you tell us the 2 factor pairs that you had?
6 and 800 and 1680.
Okay, 6 times 800, and you had 60 and times 80.
You're throwing zeros around.
Okay. Tell me what you mean, Dean, by throwing zeros around.
Because you can make at least 12 different, no, 9 different factor pairs by just throwing zeros around. You can take the zero you take a zero from the 800 and add it to the 6, and you get 60, and it'll still equal to the same amount. And say for 20 times 240, you can take the 0 from 20 and add it and make it 2,400, and it'll still be 4,800.
Awesome. I love this idea of throwing the zeros around, and I want to actually prove why that works. Thinking about what Dean just said, does anybody see one more way that we could throw the zeros around using this base fact? Ella? 600 times 8, right. So let's take a look using exponents at why this works, okay? So using what Matthew told us here, that 4,800 is 48 times 10 to the second power, how could we rewrite this equation using an exponent? How could we rewrite that using an exponent? 6 times 800. And remember, it's safe to be wrong, so it's okay to give it a guess if you're not sure. How could we try that? I see we're doing a lot of thinking. Let me model this one for you, and then I'll have you guys try these two. So I'm going to use Matthew's strategy to help me with this. And I see that I'm going to take that first number, 6, and I'm going to multiply that by 8 times the power of 10. And so, just like Dean has there, I'm going to do 6 times 8 times 10 to the second power. Yep, because I see 2 zeros here. So it's 6 times 8 times 10 to the second power. Using that, how could I rewrite 60 times 80? This is kind of tricky. How could I rewrite 60 times 80 to incorporate those zeros into there? I'm going to be thinking about what has the value of 60 times what has the value of 80. How could I rewrite that using exponents? Try it on your whiteboard. Just like Dean did on his for that last problem, try writing that on your whiteboard. Awesome. Keep that on your board, Carter. You can do that. You can do that, Matthew.
It's not even allowed.
It is allowed. Fourth graders, it's really like we're writing this in expanded form. So who wants to share out? I think Carter, I saw you had one right away. Can you tell us the equation you had?
6 times 10 in parentheses times 8 times 10 in parentheses equals 4,800.
Very good, equals 4,800. Matthew, when he was writing his, he said, what did you say? Is it okay?
Is it even allowed?
Is it even allowed to write 10 to the first power? What do you guys think?
Yes.
What does 10 to the first power mean?
10 equals 10.
It means we're looking at our base is 10, and we just have one of those 10s. So we're not multiplying it. There aren't going to be 2 that we're multiplying together. It's just 1. So we certainly can say 10 to the first power. And let's look at our last equation. If we did 600 times 8, how could we rewrite that by multiplying our whole numbers times a power of 10? Okay, give that one a try on your whiteboard. Good. Keep that on your board. Good. Awesome. Do you have a question, Matthew?
Are you allowed to have fractional exponents like 10 to the half power?
That's a great question. You certainly...
Yeah, that'd be 50.
Here's the way that I'll answer that question, Matthew. Listen up, guys. Anything is possible. Anything is possible in mathematics, truly. And so it is. However, for us, listen up, Dean, for us, we're just going to be working with whole numbered exponents for now. But anything is possible. So that is definitely possible. Who can tell me their equation? Raise a hand for 600 times 8. 600 times 8. Ella?
I got 6 times 10 to the second power in parentheses times 8.
The second power times 8. Awesome. Now, yeah, Carter.
Wouldn't it not matter if you have parentheses? Because if you're doing PEMDAS, you just, if there's multiplication, you go left to right.
Awesome. What do you guys think? Do you agree or disagree with that?
Agree.
Dean, do you agree or disagree?
I agree with that.
Yeah,
Because you can just
yeah, but still, that wouldn't change how to do it. That wouldn't change the multiplication.
So you didn't do
parentheses. So you do the problem in parentheses. Get 600. Then
Well, no,
don't you have to
do the
exponents, which is 100. So you simplify it to 600, and then you do
And then we multiply, right?
multiply.
Yeah, that's okay. So,
Get 4,800.
very good. So Dean's proved it, and yes, you're right. We technically don't need those parentheses. We could take those parentheses off. But here's a question that I have for you guys. I noticed that we said all 3 of these dimensions would work for the cheetah enclosure, right? Because they all equal 4,800. And I believe this, were we working in feet? Were we working in feet? So this was feet squared, okay. So these would all work, but the equations are all different. I want to know, how does that end up having the same value? How do all 3 of these end up having the same value? Turn and talk with the person next to you or the people next to you. How do you think these end up having the same value? What do you guys think?
The commutative property.
They still have the same amount of zeros.
Okay.
You're not really technically taking away or adding zeros. You're just moving them from one number to another.
Okay.
Commutative property.
Tell me more about that. Okay.
Because commutative property, 60 by 80 is different than 80 by 60. But it's still 4,800.
Interesting. So we could even, so you're saying we could even add another one up there. That would be 80 times 60, which technically would also work too. Interesting. Okay. 3, 2, 1. I know we had an interesting conversation over here, and I bet you guys did too. Who wants to explain in their own words? How do these all end up equaling the same value? Matthew, what do you think?
Well, by dividing one of the factors by 10, you have to multiply the other factor by 10.
Okay.
So that's technically what throwing the zeros around means.
Interesting. So for this one, we could, if we divide this factor by 10, and we multiply this factor by 10, we're maintaining the same value, but we're throwing the zeros around, like Dean said, to change it a little bit. Who can add to that? How else could we prove that these have the same value? Ella?
Well, I said there's still the same amount of zeros, they're just on different numbers.
Okay, good. So we still see 2 zeros here, here, and here. They're just on different numbers. Dean, one last thought.
I said like the commutative property, because 60 times 80 is different than 80 times 60.
Yeah,
With every other problem.
Yeah, I was talking with Matthew and Andrew, and I first was thinking it's commutative property, but then I remembered, commutative property is when you just switch the numbers that you have in an equation around. So no, it's not commutative.
It's not just commutative.
Ooh, an interesting mathematical debate.
It can be commutative if you
But the only thing is, commutative is when you take the same numbers but you switch them in an order. And 6 times 10 in parentheses times 8 times 10 to the first power. That's not the same numbers as in the top or the bottom problem. So it's not commutative.
Interesting.
But take this in mind, is 8 times 10 to the second power times 8 not the same as 10 to the second power times 6 times 8?
Listen up, guys. Dean, can you say that one more time? Andrew, listen up, because I think this is a really good question.
Would you say that 8 times 10 to the second power times 8 is the same as 10 times to the second power times 6 times 8?
Same as 10 to the second power times 6 Is this what you said?
That's commutative. But I'm saying, in the problems below where we were making all those problems, those are not commutative.
Oh, no, not all.
Technically, it's not commutative, it's associative.
Okay.
Yeah,
So this is really interesting, you guys, and I'm so glad we're having this discussion because this is exactly where I wanted this to go. I want to see, can we make, by using the commutative property and the associative property, can we make these equations all look the same? So let's think about if we wanted these two equations to look like our first one. Okay, let's use the first one as kind of our core equation. 6 times 8 times 10 to the second power. Is there a way in this equation here that we could use the commutative or the associative property to get it to look more similar to this one? What could we do, Carter?
Well, first, I was just going to point out that the bottom one is commutative to the top one.
So would you like to start, you want to start with the bottom one?
Can you take away parentheses?
As long as it doesn't change the order in which you'd evaluate it, then you can, and we already proved that we can. So hang on one second, hold on, let's let Carter share his first. So we can take those away. Now Carter, you said with this one, what could we do?
Well, I don't know how we can make the middle one.
Let's hold off on that one. Let's go to this one, like you said.
Yeah. So I'm saying that it's commutative because in the top problem there's 8 times 10 to the second power, but then on the bottom one it's 6 times 10 to the second power. And each one has the same factors, so it is commutative.
So what could we do to change this equation using what you just said? How could we make this look like this one? What would we have to change?
Slide the 6 to the very end of the equation on the bottom.
So put the 6 over here?
Yeah.
Okay. So it would look like 10 to the second power times 8 times 6. Okay, Andrew, I saw you had a thumb up. Do you want to add something different or support that?
Switch around the 8 and 10 to the second power.
So just switch these two around? Okay, let's try that. So if we do 6 times 8 times 10 to the second power using the commutative property, which one of those two looks most similar to this top one? Carter's or Andrew's? Andrew's, right? So we could do that, Carter. If we start there, though, we're going to have to do a little bit more moving around. If we move this around, though, is that the same equation as we have up here?
Oh, now I see it.
It is. So actually, by using the commutative property, that's all we had to use on this one, we can make this equation match this equation and prove that they have the same value.
Now I see it.
You see that?
You just had to take the parentheses off the middle and then switch the 6 and the 10.
Yeah. Switch the
8, the 10 and
the 10 and the 8. Very good. Now let's challenge ourselves and bring it to that middle one. What do we think we could do to make this equation look like these equations? Ella, I see you've got a strong thumbs up.
Maybe instead of doing 10 to the first power, you could put the 10 and the 10 together and make it 10 to the second power.
Ooh, okay, I'm gonna draw an arrow because I've run out of board space a little bit. So Ella said we could put the 10 and the 10 together to make it 10 to the second power because we have 10 times 10. So, and then where would I put the 6 and the 8, Ella?
It would go 6 times 8 times 10 to the second power.
6 times 8 times 10 to the second power. Can we do that?
Yes.
Is that, I'm trying to think of what Matthew said. Is that acceptable or is that, is that acceptable? Is that okay? Did we follow the rules?
Yes.
Why? Why is that, why can we do that? Why did Ella's strategy work there? Dean?
This is gonna sound ridiculous, but you can do the commutative property and you can throw around the multiplication signs. So you throw it to 10 times 10 and you take away 1 and just show it simply as a 10 to the second power.
Okay.
Then you take away the parentheses from the second one, and the 10 isn't there anymore. So, and the multiplication sign isn't there anymore. and then you do 6 times, and you add the parentheses if you want it to look exactly like that. So 6 times 8 to the second power times 10.
6 times 8 times 10 to the second power. So you're saying we're basically combining these two tens. Since we're multiplying all the way across, we can multiply those two tens together, like Ella said. And then we're just left with the 6 times 8, so it becomes 6 times 8 times 10 to the second power.
Oh yeah, and that one is not the same as the top one because there's no parentheses, and that changes the entire problem, but we get the same answer.
Now, do the parentheses in this one change the value of the equation?
No, it doesn't, but it changes the way you start out with the problem.
I see what you're saying, Carter.
Yeah, 'cause
so
in parentheses, you have to start with the parentheses, but then if you don't have, you just go left to right.
I see what you're saying. So if we put the parentheses, we would start with this part. Without it, we would go from left to right. You're exactly right. But since we're using the same operation across, we would end up with the same product, the same answer there. Really interesting work, you guys. This ended up, we kind of took a turn and ended up spending more time on this than I thought, but I think it was really valuable because what we just proved here, we proved 2 really important things. Number 1, we proved that we can use exponents, powers of 10, to help us to find dimensions or to find the factors of larger numbers. So when we were working with 4,800, I'll tell you, I actually, on my paper, I made all the possible combinations of factor pairs for 4,800, and this Post-it right here, this is my list. Those are all of the possible factor pairs. There were a ton, but I tell you, it's because I was throwing around the zeros by using exponents to help me. I started with something like this, and then I thought, wait, since I'm still just multiplying by 10 to the second power, I could change where I put those zeros. So that can help you, using exponents, can help you find factor pairs for much larger numbers. And what we also did is we proved that these equations were correct by using the properties of operations, which was really awesome that we were able to get all 3 of these to end up looking in the same equations that we could prove their value. All right. We don't have time. I was going to do one more thing, but we don't have time for that. But what I do have for you is a little extension activity that I want you guys to take back with you for your zoo project. So if you finish your zoo project, I want this to be kind of become part of it. And that's that the zoo wants to build an animal hospital off-site, not in your zoo, okay? So keep that in mind. It's not going to actually go in your zoo. They're looking to buy some land that's nearby to the zoo, okay? So that they can build a special animal hospital for all these large exotic animals. The square footage needs to be 72,000 square feet, okay? I'm going to pass this out as I explain it. So it's going to be really big, but think about, they might have animals coming from other zoos. It's going to be a really specialty animal hospital. And so what you're going to do is first choose at least 3 possible dimensions for that 72,000 square foot animal hospital, just like how we chose 3 dimensions here. Then you're going to decide which one's the most realistic. For example, if we're looking at this one, is a 6-foot by 800-foot cheetah enclosure going to be the most realistic? No. Probably not. Probably not. It would have a lot of room to run, but it would be very, very narrow. So you're going to think about which one's the most realistic, just like you did. And then, this is the most important part. This is what builds on what we just did. I want you to take your dimensions and then rewrite it using an equation with a power of 10. So showing that you can use that exponent and that you understand how that's impacting the number of zeros.
Scientific notation.
Yep, so you're going to write it using scientific notation. Okay, any questions before you head back to your desk? You guys did awesome work today.